Welcome to the Deep Dive. We're the show that takes complex ideas, digs into the sources, and tries to bring you, well, the most compelling insights we can find.
And today we are really diving deep. We're starting with something that looks simple, just a letter, but it unwraps into something huge.
Yeah, something with $1 million prize attached, potentially rewriting, basically everything about our future.
It all kicks off with X,
Yeah.
the universal symbol for the unknown. But have you ever actually wondered where it came from?
I can't say I have. I just sort of accepted it.
Right. Well, its journey is surprisingly old. We're talking over 1,200 years back to Arabic algebra and the word shay.
Shay. Okay, so what did that mean?
It literally meant thing, or crucially unknown thing. It was fundamental in those early algebraic texts.
Okay, so an Arabic word for unknown. How does that become the letter X we use everywhere?
Well, it's a bit of a linguistic game of telephone, really. When scholars, particularly in Spain, started translating these Arabic maths texts into European languages, they hit a snag.
A snag. Like what?
The she sound in she, it just didn't really exist in the same way in languages like Spanish or Latin back then. So their best approximation was to use the Greek letter K, specifically chi.
Okay, so Shay becomes represented by the Greek K. That seems like a bit of a leap already.
It does, but that was their solution. Then comes the next step. In the manuscripts, especially when translating from Arabic, often through Greek intermediaries, into Latin, that K sound, represented by chi,
Yeah.
it somehow got consistently mixed up or perhaps deliberately substituted with the Latin letter X. Maybe transcription errors, maybe printing conventions later on. It's a bit murky, but the result was clear.
Wow. So a mistranslation, essentially.
Or at least a series of transliteration choices and maybe errors. And boom, X becomes the go-to symbol for the unknown in mathematics worldwide.
That's incredible. A 1,200-year-old linguistic quirk shaping how we think about unknowns.
And it connects perfectly, almost poetically, doesn't it? From that ancient struggle to pin down the unknown with X right up to today's ultimate computational unknown.
The P versus NP millennium problem. Still an unknown. Still with a massive prize attached.
Exactly. And that's our mission today. We're going to unpack this really bold claim that P actually equals NP. We'll explore what that means. The implications are frankly staggering, and look at the discoveries pushing this idea forward. It could fundamentally change how we see computation, even our economy.
Right. So P versus NP. It sounds super technical, maybe something only computer scientists worry about, but it's more fundamental, isn't it? How do you explain the basic idea?
At its absolute core, P versus NP is about, well, time and effort, computational effort. It asks a really simple-sounding question. If you can check an answer to a problem quickly, does that mean you can also find the answer quickly?
Okay, quickly being the key word there. Give us an example we can all grab onto.
The classic one is Sudoku. If I give you a finished Sudoku grid, you can check if it's correct really fast.
Yeah, just scan the rows, columns, boxes. Take seconds. That's easy.
That's the P part, polynomial time. Easy to verify. But what if I give you a blank or partially filled Sudoku? Finding the solution, actually solving it.
That can take ages. Or feel impossible for the hard ones. Definitely not quick.
Exactly. That difficulty in finding the solution, even when checking it is easy, that's the NP side. Non-deterministic polynomial time. Problems where solutions are easy to check but seem hard to find.
Or like planning a complex trip with lots of stops and connections. You can easily see if a suggested itinerary works, if it fits all your rules.
Right, verification is fast.
But finding the absolute best itinerary, the cheapest or fastest one, out of all the possibilities, that can be computationally monstrous.
That's the essence of it. The P versus NP question is, are those hard-to-find problems, NP, actually just problems we haven't found the clever, quick way to solve yet, meaning they are also P? Or are they fundamentally inherently harder?
And most people think they are harder, right? That P does not equal NP.
That's been the strong assumption for decades. But at the very heart of this, the absolute bedrock problem is something called the Boolean satisfiability problem, or SAT.
SAT. Okay, what's that?
It's about logic. Imagine you have a complex logical statement like A must be true and D, B or C must be false and D. SAT asks, is there any assignment of true or false values to A, B, C, and so on that makes the entire statement true?
Okay, sounds abstract, but why is that specific problem so important?
Because it turns out that a huge class of those really hard NP problems, scheduling, routing, code breaking, protein folding, tons of optimization tasks, They can all be translated or reduced into a SAT problem.
Meaning?
Meaning, if you find a genuinely fast, efficient way to solve SAT, you've automatically found a fast way to solve all those other incredibly difficult problems too. Solve SAT efficiently, and P equals NP.
Whoa, okay. That raises the stakes considerably. So let's flip the coin. What if P does equal NP? What do the sources we looked at say about the implications? You mentioned alien tech.
Yeah, that's the term used because, honestly, the consequences sound like something an incredibly advanced civilization would possess. It's not just a little faster computing, it's a paradigm shift.
Like what specifically? Paint the picture.
Okay, imagine having the power to instantly design cures for any disease. You describe the disease, the parameters, and poof, the algorithm designs the molecule. No more cancer, Alzheimer's, diabetes, gone.
Seriously? Just like that?
If PNP, yes. The design process becomes computationally tractable. Same for vaccines. Or think about complete design automation. Not just software, but hardware, complex materials, molecular machines. Anything you can specify the properties for, you could potentially design optimally.
That's huge. What else?
Ensuring quality food for the entire planet becomes an optimization problem we can solve. Decomposing plastics, using custom-designed proteins, it touches everything.
And it goes further. I remember reading something about material science.
Oh yeah. Designing materials not just atom by atom, but controlling isotopes, tuning subatomic properties. This isn't just better materials, it's fundamentally new physics applications. Things like engineering inertia freedom, true weightlessness, maybe even enabling practical intergalactic travel. Stuff that's pure sci-fi now becomes potentially an engineering challenge.
Okay, my mind is slightly blown. But the sources also mention something even more fundamental changing the economy.
That's perhaps the most profound implication. If P&P is constructively proven and implemented, it strongly implies a move towards a non-monetary zero-marginal-cost economy.
Zero marginal cost, meaning it costs basically nothing to produce one more unit of something.
Exactly. If designing cures, materials, software solutions becomes computationally trivial, the cost of production for many things plummets towards zero. Scarcity, the foundation of our current economic models, starts to evaporate. Abundance becomes the default.
That is a radical idea. So how do we get from here, where P seems very much not equal to NP, to there? What's the proposed breakthrough?
Our current algorithms treat variables in a certain way, right?
Yeah, they do. Traditionally, in logic and computer science, we treat variables in things like SAT formulas as just containers, placeholders for true or false. We deliberately ignore any potential internal structure or pattern in how those trues and falses might be arranged across all possibilities.
Why ignore it?
To make the algorithms general, universal. You want an algorithm that works no matter what specific values you plug in. So you treat the variables as if they could be anything, almost randomly assigned.
But the sources suggest this view might be the problem itself, something called the inefficiency principle.
Sort of, yeah. It's framed as an alternative way to think about why NP problems seem hard. Instead of assuming PMP, this principle suggests the difficulty comes from our algorithms only seeing half the picture. They see the container aspect but miss an underlying pattern aspect of the variables.
Like trying to understand light only as a wave or only as a particle? That's a great analogy. The inefficiency comes from using algorithms designed only for one view, the container's view, when the reality might have this dual nature. We're using the wrong tool, essentially, because we didn't know the other part existed.
Okay, so the breakthrough comes from seeing that other part. This is where the team around Abdelwahab and Dabouche comes in.
Precisely. The core insight, attributed primarily to Abdelwahab's work within that team, is the discovery, or perhaps the recognition, of these hidden patterns inherent in Boolean variables.
Hidden patterns, what does that mean? Variables aren't just containers.
Exactly. They found that variables don't just hold a value, they actually exhibit intrinsic truth patterns when you look at them systematically across all possible inputs, like in a truth table. They have a structure.
Can you give an analogy for that? The sources mention one with Arabic.
Yes. The harakat or tashkil in classical Arabic. It's a system of vowel marks and other signs written above or below the main consonants. Without these signs, a written Arabic word can often have many, many possible meanings and pronunciations. It leads to an explosion of ambiguity. The harakat act like a background guide, a melody almost, that disambiguates the meaning instantly.
I see. So these patterns in Boolean logic are like the harakat for logical formulas. They guide the interpretation and prevent this explosion of possibilities.
That's the idea. They provide structure and drastically reduce the search space you need to explore when solving something like SAT.
So what do these patterns actually look like? Are they complex?
Surprisingly elegant, actually. When you list out all possible true-false combinations for the variables in a formula, the truth table, each variable column shows a repetitive binary sequence, a pattern of zeros and ones.
Like 0 1 0 1 0 1.
Exactly like that for one variable, perhaps. Another might be 0 0 0 1 1 0 0 1, another 0 0 0 0 1 1 1 1 1 1 0 0 0 0 1, and so on. It's not random at all.
And the pattern is predictable.
Very predictable. The length of the repeating block for each variable is directly related to powers of 2. Specifically, it's 2 to the power of n minus I, where n is the total number of variables and I is the index or position of that specific variable.
Okay, getting a bit technical, but the core idea is structure.
Right. And this structure, the length of these repeating blocks of zeros and ones, is inherently linked to the variable significance in binary counting. Think most significant bit, MSB, versus least significant bit, LSB. The LSB might flip every time 0, 1 is a 1, while the MSB flips only once halfway through, 0.011.1. The pattern length tells you how often it flips.
Fascinating. So recognizing these patterns is the key. How does that translate into actually solving problems faster? You mentioned FBDDs.
Right. FBDDs, free binary decision diagrams. Think of them as a super efficient way to represent and compute logical functions. They're described as materialized computations.
Materialized computations, what does that mean?
It means they're like a fundamental data structure, almost as basic as a .txt file is for text, but designed specifically for Boolean logic. They represent the entire logical function in a compressed graphical form.
Okay, and these patterns help build them.
Massively. Building these FBDDs efficiently was a major bottleneck. But Abdelwahab's team developed what they call pattern-oriented algorithms, POAs. The key one is FGPRA plus OAA, the fast general pattern-oriented resolution algorithm. By leveraging these newly understood variable patterns, FGPRA plus can construct the FBDD for a complex SAT problem incredibly quickly.
So the patterns unlock the efficient creation of these FBDD blueprints, which then lets you solve the problem fast.
That's the chain of logic, yes. It bypasses the brute force search that makes traditional SAT solving so hard for large problems.
So if this works, if PNP is demonstrable this way, what's the practical device or system that embodies this? The NDP.
The Non-Deterministic Processor, or NDP. Now, that name can be a bit confusing. It's not actually non-deterministic in the way computer scientists usually mean it. It's a deterministic machine.
Okay, so what is it then?
It's simply the practical hardware or software implementation of efficient deterministic SAT solving based on these pattern-oriented principles. It's called NDP, perhaps, because it achieves the results that a hypothetical non-deterministic machine could achieve, but it does so through clever deterministic algorithms. It can tackle problems previously considered intractable for classical computers.
So it's the engine that PNP enables. And the sources suggested it's almost a prerequisite for things like interstellar travel.
That's the implication drawn. The sheer complexity of problems involved in something like interstellar travel navigation, materials, life support, propulsion, likely requires this kind of computational power, the ability to solve massive optimization problems quickly.
And this NDP, it's not just a faster version of current computers, is it? There was talk of going beyond standard architectures.
Right, beyond the von Neumann architecture we all use, where processing and memory are separate. The idea extends to advanced materials, perhaps like those hinted at in discussions around non-human intelligence or UAP tech. Imagine materials where the computation is embedded in the material itself. The atomic or quantum structure inherently performs logical operations. Signal processing, decision-making, happening at the material level, not in a separate chip. It's like the FBCD, the materialized computation, is literally embodied in the physical substance.
The material is the computer. That's pretty out there.
It is, but it follows logically if you need extreme efficiency and integration.
And who is driving this PNP work forward now? You mentioned a foundation.
Yes, the Gridset Stiftung. It's a foundation based in Germany. They seem to be the entity orchestrating this work, maintaining the code, and importantly, filing the patents related to these discoveries.
Patents? But I thought you said.
But here's the twist. Their entire philosophy, driven by the PNP conclusion, is open everything.
Open everything?
Open knowledge, open source, open access, open data, open education. Everything they produce, the research, the code, the implementations, is intended to be totally free of any charge.
Okay, wait. They file patents but make it all free. Why?
Yeah. Because, as they argue, if P genuinely equals NP, and they have constructive proofs and working C++ implementations demonstrating this, then the inevitable outcome is that non-monetary zero-marginal-cost economy we talked about. In that context, charging money for the solution, or even claiming the million-dollar Clay Mathematics Prize for solving P versus NP becomes utterly pointless. Why would you need $1 million in a world where the fundamental basis of monetary value is dissolving?
The prize becomes useless, obsolete.
Exactly. Their open everything stance isn't just generosity. It's presented as the only logical approach consistent with the implications of their own discovery. The patents might be defensive or simply part of navigating the current system while aiming for a new one.
So this future they envision, how does it impact everyday people, you, the listener?
It's a fundamental shift from being a consumer to being what they call a prosumer, both producing and consuming value. Imagine millions, potentially billions of people connecting their existing devices, phones, laptops, servers into a global grid.
Contributing computing power.
Yes, but more than that. Collaboratively solving problems, sharing solutions instantly, because the underlying computational barrier, NP hardness, has been removed. You need a new drug design. The grid computes it. The new material. Solved. An optimized global food distribution plan. Done.
So the nature of work changes entirely. Traditional jobs.
Many would simply vanish, especially those based on information processing or solving problems that become trivial. The focus shifts.
To what?
To things that aren't easily automated or commodified by pure computation. Social capital relationships, community, trust, pursuits like sports, wellness, the arts, spiritual exploration, things that enhance human experience directly, rather than just producing goods in an economic machine. It's a vision of freeing up humanity to focus on well-being and higher pursuits, drastically reducing our ecological footprint in the process.
It's utopian, almost. Which inevitably brings us back to that term alien tech and the connection to non-human intelligence, NHI.
Right. The sources speculate, reasonably I think, that any truly advanced NHI would likely have mastered NDP-level computation. If PNP is a fundamental truth about logic and computation, they would likely know and use it.
Which explains why trying to reverse engineer suspected UAP technology feels impossible for us now. We're trying to solve an NP-complete problem with our current, presumably P-time limited tools.
Exactly. From our current perspective, their tech would look like magic or alien tech because the computational gap is so vast.
But again, we need to be clear, the sources we looked at aren't getting into why NHI might be here or interacting with us. This is purely about the technological capability implied by PNP.
Correct. It's about the how, not the why.
So let's loop all the way back to the beginning, back to X.
Our old friend, the unknown.
Yeah. This whole P vs. NP thing, the struggle, it grew out of our mathematical history, our way of formalizing logic, starting with needing a symbol like X for the unknown.
That leads to a really interesting, almost philosophical point raised in the material.
Which
could it be that NHI, assuming they exist and are advanced, never actually had a P versus NP problem?
How could they avoid it if it's fundamental?
Because maybe they never had the X problem in the first place. Maybe their path of mathematical or logical development just didn't conceptualize the unknown in the same way we did. Perhaps the way of thinking, their notation, their fundamental approach to problem solving didn't create this apparent wall between P and NP that we've spent decades grappling with.
So the P versus NP struggle might be uniquely human. A consequence of our specific historical journey with mathematics and logic, stemming from that ancient need to name the shay, the unknown thing.
It's a provocative thought, isn't it? That this grand challenge of computation might be deeply tied to our specific human context, our history of thought.
Wow. Okay, so this deep dive really went places. We started with X, the simple unknown from 1,200 years ago.
And ended up contemplating a future transformed by the claim that PNP unlocked by understanding hidden patterns in logic itself. Not just theory, but with claims of constructive proof, C++ code.
Leading to potentially revolutionary tech, cures for diseases, automated design.
And that radical shift to a non-monetary zero-marginal-cost economy, turning us all into prosumers focused on well-being, arts, social capital.
It's a future where scarcity potentially yields to abundance, driven by this fundamental computational insight. So here's the final thought for you to ponder. If our journey to solve X, culminating in tackling P versus NP, was such a deeply human path,
spanning millennia, shaped by our language, our history,
what does that mean for our future? What new unknowns will arise? And could it be that our very struggle with these problems, our uniquely human way of overcoming them, actually shapes our destiny in ways that even a civilization with alien tech might not foresee or replicate?
It suggests our path, our challenges, might forge something unique in us, something beyond just the technical solution, a compelling idea to leave things on.